started recording it. Okay. So have a look at all that work there. Pause the video and look at all that work there. Okay, our intercepts. We got a y-intercept. We let x equal 0. And I think that's it. We don't have another x-intercept. We can't let y. That's it. So those are intercepts. Domain. What's the domain of this function? And believe me, if you don't say the domain, you can get yourself into all kinds of problems, especially when you get to radical functions. Well, our domain, we've got domain restrictions, all reals except x can't equal plus or minus 1. Oh, we didn't answer the asymptote question because I only looked at vertical asymptotes, and there's another kind of asymptote. How do you find the horizontal asymptotes? So for horizontal asymptotes, you're looking for the limit as x goes to infinity for this function. Do you know what it is? Just from looking at that. The power of the variable is the same in the numerator and the denominator. Look at the ratio of the leading coefficient. What's that answer? Okay. What about as I approach negative infinity? Well, it's an even function. I'm going to square those numbers. It's also going to be 2. So we've got a horizontal asymptote at x equals 2. Did I say x? At y equals 2. Okay, and we also had that one and only intercept. Okay, you may already kind of know what this looks like. Have we done everything? The range of this function, I guess the range is, we're only going to get y values bigger than 2 or less than 0. Okay, then the first derivative. So f prime at x is going to give us our regions of decrease, increase, our max, and our min. So what's f prime at x? Well, I guess I'm going to need a quotient rule. So on the bottom, I've got the denominator, x squared minus 1 all squared, and then I've got low, d high, less high, d low. Okay, that wasn't so bad at all. Okay, and let's just simplify this. I've got 4x cubed minus 4x, subtract 4x cubed, all over x squared minus 1, all squared. And it looks like my 4x cubes are canceling. And here's my first derivative, negative 4x over x squared minus 1, all squared. And with our first derivative, we find our critical numbers. Critical numbers occur when our derivative is either 0 or undefined. Okay, please note that these critical numbers are your asymptotes, at which point your derivative is undefined. Why is that derivative undefined? Because as you get closer and closer and closer to 1, your function goes up, 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 up. What do you think the slope of that line is? As it goes up, the slope of that line is infinity. Right? You can't take the slope of a vertical line. It's undefined. That's why you're getting this critical number. So you're not going to be looking for a max min here. It's not even in the domain of the function. You're only looking for a max min here. Okay, so let's look at 0, -1, +1. Okay, so what happens if I choose a number between 0 and 1 and put it into my derivative? Denominator's always positive. The sign's gonna come from the numerator. So if I put a positive number here, I'm always gonna get a positive. And if I put a negative number in, I'm gonna get a negative. So my function is decreasing from -infinity to 0, and then it's increasing from 0 to infinity. And if it was decreasing, and now it's, I feel like I did that backwards. Hold on. I should look at my work when I do this. It's increasing. I got it backwards. Sorry. Okay. So my intervals of decrease. So looking here at my second derivative, then the denominator is always going to be positive. If I put a negative number in, a negative times a negative is going to give me a positive. If I put a positive number in, I'll have a negative times a positive, which will give me a negative. So this function is increasing from -infinity to 0 and decreasing from 0 to infinity, which tells me that 0 must be a local max. Okay. Okay, and then maybe I'm just going to keep track of these numbers as we go. Here's x, and here's f at x. So I've already found vertical asymptotes at -1 and at +1. So the function's not defined there. And at 0, and if x is 0, we can see y is 0. My xy intercept, I have a local max. And now we need to look at the second derivative. So what is f double prime at x? We're going to look for where's this concave down, concave up, what are the inflection points? Okay, so the second derivative. Look here and take the second derivative. I'm going to use a quotient rule. X squared minus 1 squared all squared is going to give me x squared minus 1 to the 4th. Taking the derivative of this, then, it's going to be low, x squared minus 1 all squared, d high, which is going to give me -4. Subtract -4x times the derivative of the bottom, which is going to be 2 times x squared minus 1, chain rule, times 2x. Okay, and then let's simplify this. So denominator, x squared minus 1 to the 4th. Did I factor that? Yeah, let's take out our GCF. So we do have a GCF here of x squared minus 1. And also going to take out a GCF of 4. Okay, so if I take out that first, I think I'm going to run out of room here. If I take out that first x squared minus 1, 4 bracket x squared minus 1, then it's going to go into this first term, negative x squared minus 1 times. So the negative coming from here, and then I've got the x squared minus 1, and I've already taken out the 4. Okay, plus I took out the 4. There's a 2x and another 2x. There's going to be a 4x squared. And I took out the x squared minus 1. So then collecting up my like terms in front of here, or canceling off my common factors, I've got an x squared minus 1 canceling one of those on the bottom. So denominator, x squared minus 1 cubed. And here I've got a negative x squared and a positive 4x squared is going to leave me with a 3x squared. And I've got a negative negative, which would be plus 1. And be really careful with those signs. Okay, so there's my second derivative. The critical numbers here, where the numerator is 0, could that numerator be 0? Why not? Yeah, because you can't take the square root of a negative number. You'd end up trying to solve negative 1 over 3 plus or minus the square root. Okay, so there's no critical number on the top. You got a critical number on the bottom, plus or minus 1. And you could see that those are, once again, your vertical asymptotes. Okay, so from your second derivative, here's negative 1, here's positive 1. From your second derivative, we can see that the numerator, no matter what we put into it, is always going to be positive. The sign is going to come from the bottom. What happens if I put a number in between, like 0? I'm going to get negative 1 cubed. What if I put a big number in, like 10? I'm going to get a positive. Or negative 10, I'm going to get a positive. So this function is concave up from negative infinity to negative 1, and from 1 to positive infinity, and it's concave down in between negative 1 and positive 1. Do we have inflection points? You say, oh, an inflection point is where a function changes from concave up to concave down, or vice versa. Are these inflection points? How many of you agree? How many of you disagree? What's the other criteria for an inflection point? The inflection point has to be in the domain of the function, or it's not an inflection point. Okay, so we say that we have no inflection point. Okay, a vertical asymptote can't be your inflection point. And I think this is it. That's all we have to do. So my function is increasing from from negative infinity to 0. It's just increasing. How am I going to graph a function that increases from negative infinity to 0, and I have a horizontal and a vertical asymptote? Pretty much this is the only thing it could be. It's got to look something like this. Oh, and it keeps on increasing all the way to 0. So increasing and then increasing. So this function's still increasing. Do you see how it's increasing all the way up, up, up? And it started way down here and it's still increasing. And when I hit 0, my function starts to decrease. And it still decreases ever after that. You see that this is concave up, this is concave down, and this is concave up. I have no inflection points because those critical numbers were vertical asymptotes.